Now lecture number 4 PDF file that I uploaded, I realized I made a mistake. There was a typographical error, writing error, when I was talking about anti-symmetric matrix. I wrote Aij of anti-symmetric matrix as minus of Aij of anti-symmetric. No, that's not correct. This is correct. Aij is minus Aj for an anti-symmetric matrix when I is not equal to j. Aij is minus Aj. So this order was wrong. I have corrected it, and in the uploaded PDF that correction shows. So do take notice of that. All right. So what all I completed in the previous lecture? I talked about gradient of a tensor, gradient of a tensor. I talked about divergence of a tensor. Then I talked about Laplacian of a tensor. And I talked about this operator which is called the advection operator. I gave one example for each of these quantities. What do we do next? This I leave. So far, for last 2 days, I have been expressing every tensor in a Cartesian coordinate system, and later I also restricted that Cartesian system to be one which is embedded to the reference frame also. Now I am going to talk about expressing tensors in a cylindrical polar coordinate system. So when you are trying to study fluid motion, we will come across some flow fields in which a cylindrical polar coordinate system would be better than a Cartesian coordinate system. The tensors will remain unchanged. Tensor does not depend on any coordinate system. However, the tensor operations, the way we are performing, that will depend on working coordinate system. Sometimes you will choose cylindrical polar coordinate system, and thus I want to tell you how to express these tensor in a cylindrical polar coordinate system. In APL 100, you have studied about cylindrical polar coordinate system. I am going to quickly review what we learned there. So even before we define a cylindrical polar coordinate system, we do need a frame fixed Cartesian coordinate system in the background. It is still required. That coordinate system has been shown here, and you can think of a frame also like something like this. Okay, this is the frame. Cartesian coordinate system is fixed to that, and then on top of it we define our cylindrical polar coordinate system. So if P is a point of interest, then the cylindrical polar coordinate system has these coordinates. I am reviewing r, theta, z. And the unit vectors of a cylindrical polar coordinate system are denoted by as er, e theta, and ez. So what are these quantities r, theta, z, and how are these unit vectors defined? So if the point of interest is at this location, we drop a perpendicular, right, on the plane of x1, e1 and x2, e2. Let's call this point P prime. And then you connect the point P prime to O. This distance is r, the same r which is appearing here. and a unit vector which will be along this P prime O will be ER. Now mind you, when writing R, sometimes I use this R, sometimes I use this, sometimes I use this. It's unintentional. I don't want to use different types of R. But it turns out in the flow of writing, I end up writing them in different ways, but they are all the same. They are all small r. Okay. So this is my vector ER. And then what is E theta? E theta will be a unit vector which is perpendicular to ER and it is directed in this manner. I mean, if you go from x1 E1, start measuring, and the angle that this O P prime is making with x1 E1 axis, we call this theta, and the direction of E theta is in the direction of increasing theta. Direction of E theta is in the direction of increasing theta. All right. So two unit vectors I have in this way, and also I have described the two coordinates r, and now theta I have described. What is z? Z is this distance, right? Z is this distance. And what is Ez? Ez is a unit vector which is same as the unit vector E3 of the background Cartesian coordinate system. Right. So Ez is same as E3. Z is P prime is the point on x1 E1 x2 E2 plane where perpendicular from drop from P meets the plane, right? ER is along the vector position vector R prime P prime O, right? That is ER. R is the magnitude of R P prime O, always greater than or equal to 0. Theta is the angle that R P prime O makes with x1 E1 axis. E theta is perpendicular to ER and is directed okay, and Z is positive or negative distance of P from P prime. So generally distance we say is always positive, but I am putting this extra thing, positive or negative. So if P is above the plane of x1 E1, Z is greater than 0. If P is not here, but P is lying below the x1 E1 x2 E2 plane, we will have negative Z. I will put this under quote. Okay, so in this way you define all these 3 coordinates and 3 unit vectors. Now, in cylindrical polar coordinate system, your independent coordinates are r, theta, and z. They are not x1, x2, x3. And the unit vectors are, as I drew earlier, er and e theta and ez. Now, if you come across derivatives like what I have shown here on the left hand side of the screen, we will have to be careful that some of them may be non-zero. This is what I was talking about in my previous class, that when your working coordinate system is Cartesian, whenever you come across things like that, they were all zero. In general, del EI del xj was zero. Frame fixed Cartesian coordinate system. Right? Here in the cylindrical polar coordinate system, all of them are not zero. Del ER del R will still be zero. Del ER del theta will be non-zero. Please keep in mind, and that actually becomes E theta. In APL 100, you would have derived it. In my problem set 1, I have given one problem in which you will have to derive it again. So that will be a good revision of what you have done. Okay. Then you come to del ER del Z. Del ER del Z, that is still zero. Okay. The next one, del E theta del R, still zero. But del E theta del theta turns out to be non-zero, and again it can be derived and shown that it is actually minus ER. The rest of them, derivative of theta with Z, derivative of EZ with R, derivative of EZ with theta, derivative of EZ with Z, all are zero. So most of them are still zero, but 2 are non-zero, and they can have consequences when you are trying to write, say, the gradient of a tensor, divergence of a tensor. You will have to pay attention to these non-zero quantities. Okay. Now let's try to express, with all this understanding and review, let's try to express a tensor in cylindrical polar coordinate system. I've again drawn these ER, E theta, and EZ, and P is a point R, theta, Z coordinates. Now a word of caution, very important. We will not use Einstein's summation rule when the working coordinate system is cylindrical polar. There is an advanced version of Einstein's summation rule that can be employed even for cylindrical polar coordinate system, for that matter any coordinate system. However, we are not going to study those advanced aspects of Einstein's summation rule. We will, whatever we have learned about Einstein's summation rule in the morning, we are going to restrict to that, and keep this in mind that with that much information, you must not use this Einstein summation rule for cylindrical polar. So in cylindrical polar, if you have to express a tensor, a vector, be ready to write full expressions. Whether it is 3 terms, 9 terms, 27 terms, whatever it is, you should be ready to write the full versions. Okay. So if I have a vector A, some vector A in space, okay, and if I want to express it in Cartesian coordinate system, of course I will write this much. All information has been conveyed. But then I insist that I want to write that in the cylindrical polar coordinate system. How will I write it? That will be written as, in general, it will be written as this. So I'm not using numbers. You see, 1, 2, 3, I'm not using. I'm using subscripts R, theta, Z. And this is one reason why Einstein's summation rule cannot be applied here. Because there you need numerical indices. Here the indices are not numbers, but the symbols of the coordinates themselves. So in this course, we will write it like this. Again, AR, A theta, AZ are simply scalars. Okay, they can be greater than 0, less than 0, or 0 also, but only scalars. There are names, specific names for these components. Napier 100, we talked about this. AR is called the radial component of vector A expressed in cylindrical polar coordinate system. If I have to make a sentence out of it, A theta is called the transverse component of A. Transverse component ditto of the vector A in cylindrical polar coordinate system. AZ is called the axial component. Axial component of A. Okay. So a vector will have 3 scalar components, and this would be the expression. Moving on, now I want to express a second order tensor in cylindrical polar coordinate system. Recall, if I allowed you, if somebody allows me to use Cartesian coordinate system, this is it. That's all. Tij, Eij, very compact, not in cylindrical polar. So here, what would be the expression of it? What would be the expression of it? Again, we will have to use dyads. Dyads constructed with the unit vectors of cylindrical polar coordinate system. Right? Dyads like ER, ERE theta, EREZ, and so on. 9 such dyads will be created, and thus the full expression of T, a second order tensor, would be like this. And I will have to spend time writing everything here, because I am not using index notation anymore. TRR, ERER, TR theta, ERE theta, ERZ, EREZ. More terms. T theta R, E theta ER, T theta theta, T theta Z, E theta EZ. 6 taken care of. 3 more. PZR. And finally, TZZ, EZ, EZ. That's the full expression of a second order tensor. ER, ERE theta, EREZ, theta R, theta theta, ZR, theta, ZZ. all right, where of course all these t's which are appearing there, they are just scalar components. TRR, TR, theta, all the way to TZZ are scalar components of T in cylindrical polar coordinate system. All right. Similarly, if I asked you to write a third order tensor in cylindrical polar coordinate system, I hope all of you will be able to do that. That would be something like TRR, ER, ER, ER to begin with, and then it will be RR theta, ER, ER, E theta, and so on, all the way to 27 terms if T is third order tensor. Okay, we'll have to write it like that. Later in the evening or tomorrow morning, when you pay attention to my tutorial set, the problem set, you will find that most problems are actually coming from related to cylindrical polar coordinate system, and most problems are also related to the Nabla operator, and I am asking you to express divergence, advection, gradient of tensors in cylindrical polar coordinate system. So the exercise has mostly, the most problems are from cylindrical polar. I hope that exercise will help you consolidate the concepts that we have learned so far in the lecture. Okay. If you have any questions, feel free to type in there. Okay. Moving on. What do we do next? This I have already said. You must pay attention to these things while solving the problems. So repeated information here. Next. So I'm done with tensors. If you go to my course document, you will see that the first topic was on tensors. We are done with that. Now we are going to start the new topic, which is description of fluid motion. How do we describe fluid motion? These are the options that we have. We can either have a molecular description of fluid motion. I will explain in a little while what it means. Or you can have what is called the continuum description. We'll explain. I'm trying to give you the big picture before I start getting into details again. So two options to begin with, either you use molecular description or you use continuum description. Within the option of continuum description, there are again two options. One is called the Lagrangian description, and the other is called Lagrangian description, and the other is called the Eulerian description. What are the similarities, differences between these descriptions? What are the advantages, disadvantages of these descriptions? We will go over all that. After going over all that, we will realize that the most appropriate way, most convenient way of describing fluid motion will turn out to be the Eulerian description under the heading continuous description. All right, that will be the final conclusion of this topic. But I will try to convince you why that is the best way for us to move forward. Okay. Let's first talk about the molecular description of fluid motion. What do I mean by molecular description? See, at the end of the day, we all know that all matter is comprised of molecules. right? Whether it is a solid object, a liquid or a gas, there are molecules down there. So one approach which seems very straightforward actually is to say that I want to describe fluid motion and every fluid is comprised of molecules. Why don't I write this equation for each and every molecule and track the motion of all those molecules? And if I can track all the molecules individually, indeed I have described the fluid motion, because whatever motion is being observed, and there are molecules which are actually moving. What is this equation? This is a very familiar equation. This equation is Newton's second law, right? Where I have used some symbols and indices, and do not confuse these indices with an index notation. There is no index notation implied here. No index notation implied here. I is being repeated twice, but there is no summation implied. No index notation used here. Here I means something else. What it means? When I write IF vector, this quantity, I am basically saying that I am talking about net external force on the ith molecule, right? After all, there are numerous molecules, like the picture I have shown here. If you're talking about liquids and gases, you are not dealing with one molecule. You are dealing with several of them. So I is the counter of molecules. So this equation is being applied with system being the ith molecule of all the molecules. Left hand side is the net external force that acts on the ith molecule. What do we have on the right hand side? I have Mi, which is the mass of the ith molecule. And I have this term symbol Ia, small I, bar, big I, APL 100 notation. This is the acceleration vector of the ith molecule. And this big I is the inertial reference frame. All right. So equation is known. I know everything is made up of molecules. Why don't we apply this for each and every molecule? And that will become what we call as the molecular description of fluid motion. Now this conceptually is very straightforward. However, it has limitations. This method has limitations, or rather I would say there are two major challenges you will face if you try to use molecular description of fluid motion. What are those challenges? The first challenge is that the number of molecules that you will be handling is too high. Too high. How high? How high I am talking about? And before I remind ourselves how high it is, why am I worried about the fact that the molecules are there are numerous molecules? See, if you are willing to solve this equation, the equation itself is simple, but if there are numerous molecules, you will have to do this computation numerous times. If you are using a computer will be overloaded to repeat this calculation for numerous members, right? So in that way, the computational overload, it has a large computational overhead. Okay? Now I come to the question, how high? You are aware of this, how high it could be. Suppose I focus on 1 meter cube of fluid. So you have a reference frame here, inertial reference frame, there is fluid. And in this fluid, I am considering a volume, a part of the entire domain, part of the domain of the fluid flow. And let that domain have this volume 1 meter cube. Now, if this fluid is air at room temperature, one atmospheric pressure, and if I call this number as I call n as the number of molecules in 1 meter cube. So why am I choosing 1 meter cube? Because your domain will be like that, 1 meter cube, 5 meter cubes, right? If you are considering a car moving on a highway, the volume of the domain is what, like 2 meters, 3 meters cube. So similar order. How high is this number? This is of order 10 to the power 23 molecules. How am I getting this number? Avogadro number I'm talking about. It's like 10 to the power 23 molecules of nitrogen, oxygen combined. Right? Mainly it is nitrogen and oxygen. Is it high? It is very high, very, very high number. And suppose it is water, fluid is water. It is a river flow, and you take 1 meter cube, you grab 1 meter cube of water. How many molecules of water will be there? N will be, according to my references, number of molecules will be 10 to the power 29 molecules. After all, water has a higher density, so you would expect that in 1 meter cube there will be more molecules. Indeed, there are 10 to the power 29 molecules, very large number. That's a challenge in molecular description. Okay, I don't like this. So molecular description is like one down, a disadvantage. The second problem or the second challenge with the molecular description is that our probes do not sense or interact with individual molecules, but with a bunch of them at a time. After all, we will sense, right? We will sense the fluid flow. We are perceiving the fluid flow. We can either perceive it through our eyes, we just watch the fluid flowing, or we can put probes, whatever probes and sensors we have designed over these years, right? We can perceive, sense, interact with fluid only through our probes. Let's consider a probe, a typical probe, which may measure velocity or pressure. You call it a probe, you call it a sensor. Some of these you will use in our labs when you do experiments. Whatever probe you use, velocity or pressure sensor, it will have some dimension, right? That's what I have tried to show here. So there is a fluid flow here, and I have inserted a probe with which I am trying to say measure velocity or pressure. So probe will have a surface area through which it interacts with the fluid. That surface area I'm showing here, and I'm telling you that the best probes that we have, it will still have dimensions of like 1 mm by 1 mm, which is quite small as perceived by our eyes, but still it is finite. 1 mm by 1 mm. Now, if you try to sense the fluid motion by a probe which has this much size, the question is your probe interacting with an individual molecule, or is it interacting with a bunch of molecules at a time? So I pose this question: how many molecules of water or air is my probe is interacting at a given instant? Statistically speaking, on an average, like you do 5 measurements or 10 measurements. On an average, you tell me that during one measurement, how many molecules did my probe interacted with? Okay. That number turns out to be what I have here. Let's first pay attention to this part. We can perform a crude estimate. I am not presenting that way of estimation here. I have left that part. But we can perform a crude estimate at room temperature. If the fluid is water, how many molecules of water interact with a probe of 1 mm by 1 mm size at a given instant? That crude estimate tells me that that number is 10 to the power 12 molecules. And if it is air, my crude estimate tells me that it is 10 to the power 8. Both are very large numbers, right? So our probes cannot sense individual molecules, and that is why there is no point, or it doesn't seem seems like a very good idea to actually track individual molecules. Even if I track them on a computer, or theoretically, if I have to perform experiments, or when my engineering system is actually interacting with the fluid flow, we are not going to sense individual molecules at all. We are going to sense bunch of them. All right. So because of these two reasons, we do not like molecular description. We have to think of something else. Okay. So my conclusion as far as the molecular approach is concerned, that it is not preferred. Number one, too many molecules to track. And the second reason is our probes anyway do not interact with individual molecules. So we will not use this. So on this slide, I did put this picture. You see why this. It's not touching the huge space between molecules. I'll come back to it later. Right now, it doesn't seem very relevant. Fine. The molecular approach I am going to drop. So the next option is to go for what is called the continuum description of fluid motion. I want to show you this slide again. This I hope I have explained to a good extent that why this is not a good way of describing fluid motion. Now I will talk about this continuum description. The so-called continuum description of fluid motion, it pretends that the molecules don't exist at all. It doesn't see, the continuum description doesn't see a fluid in terms of molecules. Continuum description says that the smallest entity in a fluid flow is what we call as a fluid particle. It defines its own entity, the continuum description. Fluid particle. I will use this acronym FP. Numerous times I will talk about, refer to fluid particle, and in my notes you will see FP appearing here. This is the smallest entity. It is assumed to be a point mass. It's a point mass. In the continuum description, this is a point mass. No dimension whatsoever. But please keep in mind that a fluid particle is not a molecule. This is a confusion we often get into. Fluid particle is not a molecule. As I said earlier, continuum description has forgotten molecules. Okay? So there is a fluid flow, there is this inertial reference frame. In continuum description, you consider a point mass, and that is a fluid particle. Indeed, continuum sense, it has no dimension. But if you talk in terms of absolute scale, a fluid particle does have dimension. And that dimension would be on absolute length scale. Will have dimensions like 10 to minus 4, 10 to minus 4, 10 to minus 4 meter cube, and then I will put a number here, eta, where eta is close to 1. Eta is a number close to unity. On absolute scale, this is the dimension of a fluid particle. Okay. But for continuum description, we will not worry about this part. On absolute scale, what is the dimension, we will never worry about in continuum description. We will just consider this to be a point mass. And once we have considered a point mass, calling that as a fluid particle, then we will have velocity. We will associate a velocity with that fluid particle. We will use this symbol VPI. VPI is what? Velocity of FP, P, this fluid particle, with respect to frame I. As units, of course, meters per second. We will associate a density with this fluid particle, rho P, density of the fluid particle, density associated with the fluid particle. kg per meter cube. We will associate a temperature we will associate a temperature with this fluid particle. Unit will be Kelvin. We will associate pressure with this fluid particle. All right. We would like to describe the fluid motion in terms of these fluid particles, and in turn in terms of these new quantities that I am having: density, velocity, temperature, and pressure. And we will like to have governing equations of these quantities rather than individual molecular motion. As I said, we have turned a blind eye to the fact that there are even molecules existing there in continuum description. Now, this continuum description is actually an approximation. It may not be sensible in all situations. I want to make an attempt to explain why in certain situations this may break down. Let's look at this figure that I'm showing here. Different states of matter have different types of arrangement, or rather distribution of molecules within it. In a solid, the molecules are closely packed, as shown here. They are touching each other, right? They are all touching each other. I guess this is what I wrote here. Now I remember. I have written here. So in solids, molecules are touching each other. Molecules may vibrate. They do vibrate. Left, right, up, down. These molecules will do. There is that much degree of freedom. But if you take the time averaged picture of a solid, we realize that the molecules do not move from where they were. Even if they move leftwards, they vibrate, come back. Left, right. So if I take time average, their location will be the same at all time instants. In contrast, liquids have molecules still touching each other. Most of the molecules are still touching each other. That's what is shown in this diagram picture. They do touch each other, but they do move around substantially also in liquids. A molecule which is at time t1 here, after some time that molecule may find its way and it may appear here. Same molecule, let's call this molecule as alpha molecule. So the alpha molecule of a liquid at T1 will be at this location. At some time later, the alpha molecule will find its way here. It sneaks out. I mean, it has a way to move around, even though molecules are touching each other, right? On the other extreme, we have a gas in which molecules are most of the times not touching each other. Most of the times. For sometimes they collide. Yes, molecules are colliding, but that collision happens very fast. I mean, the duration over which they interact with each other is very small. They collide, and for a large time they travel uninterrupted, and then have another collision, impact, another impact, then again travel for some distance. That's what molecules do in a gas. So that's what I am saying. They are not touching each other most of the time, and they move around indeed substantially. Again, if this is the beta molecule at T1, you come back at T2, beta molecule would have moved very far. It might have even gone out of this box, but I will still say that within the scope of this diagram, I will say maybe beta at T2 will come here, right? So this picture will help us understand what the limitations of this continuum description is. Let's go back to this slide. Let me define a length L, which I am calling as the distance between the centers of two molecules, neighboring molecules, nearby molecules. And I'm saying it's an average distance. Of course, this distance keeps changing all the time. But if you take a time average and get a statistical estimate of the distance between the centers of two nearby molecules, it will turn out that in liquids, this L will be almost the same as the diameter of the molecules. That you can see here. This is a molecule, center here, center here. Since they are touching, this distance will be the diameter of the molecule. However, in gases, that distance, the distance between two nearby, this distance between the centers of two nearby molecules will not be the diameter of the molecules. It will be the mean free path of the molecules. What is mean free path? It is the average distance that a molecule travels before it collides with another one. Right? That is called the mean free path. If I try to draw the mean free path, it will be something like this. This is the mean free path, or something that represents mean free path or is close to mean free path. Clearly, it's much more than the diameter of the molecules, because in gases we know there is so much hollow space. Most of the space is hollow actually. Okay, I'm using the same length scale to represent two different things in liquids and gases. It is the distance between the centers of two nearby molecules, but in liquid it is diameter of molecule, and gases it is mean free path. And here is the limitation, or the condition under which continuum approximation will break down. For continuum validation to hold good, L should be much less than 10 to the power minus 4 meters, which is the dimension of our probes. L should be much less than the dimension of our probe. If this condition holds good, your continuum approximation is valid. It turns out that on Earth's surface, most engineering flows do follow this condition. In fact, liquids will always follow this condition. Liquids will have no problem violating. Liquids have no business violating continuum approximation, because this is very well true. You can compare, you can get some data, get the length of diameter of a water molecule. You will see that that will be much less than 10 to the power minus 4 meter. In gases at room temperature near Earth's surface, the mean free path will also be much less than 10 to minus 4, and that is why continuum is fine for flow of air past a building, flow of air past a car, flow of air past any other object near Earth's surface, flow of air past an aircraft flying, your commercial aircraft, still valid. But there are some exceptions. The exception is what I am trying to show here with these figures. I am showing a spacecraft that is re-entering the atmosphere, or a missile warhead that is re-entering the atmosphere. Okay, so when a spacecraft is re-entering, it has gone out in space and then it wants to come back. When it tries to come back, initially the atmosphere is very thin. Atmosphere is very thin. Re-entry vehicles. Thin atmosphere. In thin atmosphere, what will happen? The mean free path of the molecules, if you go back here, this distance what I'm talking about will be very large. Thin atmosphere, very few molecules are there. An aircraft encounters one molecule, then it waits for like 20 seconds to collide with another molecule. Mean free path is very huge. And when mean free path becomes very huge, you will have this condition violated. L is not less than 10 to the power minus 4 meter, not much less. If this is not valid, you cannot use these continuum ideas that I am trying to introduce here. You cannot define a fluid particle. You cannot talk about velocity of a fluid particle or density or temperature or pressure. All these things will be not applicable. In that case, you have to do some special things. Those special things will be related to the molecular description. You will have to go back. Thankfully, in this course, we are not going to worry about this. In this course, we are going to only talk about applications of flow of water, air, liquids, gases near Earth's surface. This condition is very much valid. We are going to stick to the continuum description in this course. Okay. If you want to know more about this, you will have to take specialized courses. What you learn in this course will not be good enough. That brings me to the last slide of this class. Summary. This not going to be used, this going to be used, but then two options are there, Lagrangian and Eulerian. What are these and which one is better for us? We will discuss that on Friday. I stop here.